Welcome to the world of ChronoLentis-Phi, a revolutionary leap in aerospace design. This is not just another vehicle, it's a temporal lenticular craft, engineered to manipulate the very fabric of time and waves. At its core, the CL1-Phi mirrored Seraphim is a fusion of advanced materials, golden ratio geometry, and cutting-edge temporal physics. In this series, we'll explore how this craft scrambles its own history, evades detection, and even extracts energy from the environment. Let's begin our journey by understanding the foundational vision behind this unprecedented system. At the heart of the ChronoLentis-Phi craft lies a temporal metamaterial shell. This shell isn't just a physical barrier, it's a programmable boundary that can reflect electromagnetic and acoustic waves in time. Inspired by recent CUNY experiments, the shell can flip the order of incoming waves, making them retrace their history with altered frequency. This means the craft can scramble its own interaction timeline, effectively hiding its presence and confusing any attempt at detection. The shell's lenticular, multi-layered structure is meticulously engineered using Fibonacci sequences for optimal field control. The craft's hull is not randomly layered. Each shell is positioned at radii determined by the golden ratio, following the formula Rn equals R0 times IIn. This Fibonacci structuring isn't just for aesthetics, it's a functional choice that disrupts coherent detection, supports multiband resonance, and distributes stress evenly. By aligning both spatial and temporal features with the golden ratio, the craft achieves a unique blend of stealth, structural efficiency, and optimal field manipulation. This mathematical approach is a cornerstone of the ChronoLentis-Phi design philosophy. Temporal drive sequencing is at the heart of the craft's programmable boundaries. By pulsing variable energy inputs, voltages, currents, acoustic drives, and plasma bias in Fibonacci-timed sequences, the craft creates quasi-aperiodic temporal boundaries. These boundaries frustrate external sensing, lock in internal coherence, and enable stealthy operation. The timing, Tn, is proportional to Fn, ensures that no two pulses are alike, making the craft's presence nearly impossible to correlate or track. The concept of time reflection is central to the ChronoLentis-Phi system. Inspired by CUNY's laboratory breakthroughs, the craft's metamaterial hull can rapidly flip its properties, causing incident electromagnetic or acoustic waves to be reflected in time. This means the wave retraces its path backward, with its frequency content altered. For the craft, this translates to scrambled radar returns, nullified shock signatures, and a history that can be rewritten on demand. Time reflection is not time travel, but it's the closest thing in practical physics. Within the lenticular hull, the craft establishes coupled standing waves, electromagnetic, acoustic, and plasmonic, all sharing programmable boundary conditions. These standing wave cavities can be flipped in time, allowing the craft to partially rewind or advance wave histories relative to the external environment. This temporal cavity is the engine room for energy storage, directional thrust, and field coherence, making it a multifunctional core for propulsion and stealth. Propulsion in the ChronoLentis-Phi craft is achieved through temporal asymmetry. By biasing time reflection events, making them stronger on one side of the hull, the craft creates momentum gradients across its field configuration. This results in non-Newtonian seaming motion, where the craft can accelerate or change direction without traditional thrust. The manipulation of time boundaries becomes a new form of field propulsion, opening doors to exotic maneuverability. After any maneuver or interaction, the craft can initiate an erasure sequence. This involves rapid, multi-shell time reflections that overwrite the electromagnetic and phononic history in the local environment. To external observers, the data appears as incoherent noise, making it impossible to reconstruct the craft's presence or actions. This post-event erasure is a powerful tool for operational secrecy and legacy trace removal. On land, the craft's acoustic metamaterials suppress shock waves and seismic signatures. This allows for stealthy motion across terrain, leaving no detectable footprint. The plasmonic and dysprosium layers stabilize fields even in dense media, ensuring that the craft remains hidden from ground-based sensors and maintains operational integrity in challenging environments. In the atmosphere, the craft exhibits classic UAP-like behavior, rapid accelerations, low drag, and radar confusion. Acoustic attenuation is achieved through Fibonacci-structured phononic lattices, nulling sonic booms and pressure wakes. Time-reflected electromagnetic waves further scramble radar returns, making the craft nearly invisible to conventional detection systems. Underwater, the craft leverages its acoustic core for ultrasonic cavitation and hydrodynamic stealth. Modulated acoustic metamaterials suppress pressure waves, allowing for silent motion and minimal drag. The plasmonic skin manages electromagnetic interactions, ensuring that the craft remains undetectable even in complex marine environments. In space, the craft's plasmonic and electromagnetic time mirrors become the primary tools for stealth and propulsion. Temporal cavities are used for energy accumulation and release, enabling pulsed temporal thrust cycles. The craft can adapt its field boundaries to match the vacuum resonance, achieving non-Newtonian motion and energy efficiency in the harshest environment. The ChronoLentis-Phi craft is designed for universal adaptation. Its modulated standing wave envelope can adjust to local space-time curvature, ensuring seamless transition between land, sea, air, and space. This universal mode is achieved by dynamically tuning the temporal and spatial boundaries, maintaining optimal stealth and performance regardless of the environment. The mathematical backbone of the ChronoLentis-Phi system is built on golden ratio shell spacing, Fibonacci-timed pulse trains, and temporal boundary equations. These mathematical constructs are not just theoretical. They directly inform the craft's geometry, energy sequencing, and field modulation. By embedding these principles into every layer, the craft achieves a harmony of stealth, energy efficiency, and operational flexibility. The use of golden ratio shell spacing is a defining feature of the craft's hull. Each layer is positioned at a radius determined by Rn equals R0 times IIn, where II is the golden ratio. This arrangement disrupts regular detection patterns, supports multiband resonance, and optimizes the distribution of mechanical stress. It's a mathematically elegant solution that delivers real-world stealth and resilience. Temporal boundaries are governed by precise mathematical relationships. The key equation, ET plus equals alpha ET9, describes how electric fields behave across a time-reflective boundary. This equation is central to the craft's ability to flip wave histories and control field interactions. By mastering these equations, the ChronoLentis-Phi system achieves programmable stealth and energy manipulation. The time-inversion operator, TET, equals E-T, is used within the standing wave cavity to reverse wave histories. This operator is not just a mathematical curiosity, it's a practical tool for energy storage, directional thrust, and field coherence. By applying this operator, the craft can manipulate the temporal order of wave interactions, achieving effects that appear to defy conventional physics. The standing wave cavity is mathematically described by coupled equations for electromagnetic, acoustic, and plasmonic modes. These equations define how energy is stored, released, and manipulated within the cavity. By tuning the boundary conditions, the craft can control the coherence and directionality of these waves, enabling advanced propulsion and stealth capabilities. The hull of the ChronoLentis-Phi craft is a masterpiece of layered engineering. It combines a plasmonic metasurface skin, Dysprosium magnetic lattice rings, an acoustic metamaterial core, and a temporal modulation layer stack. Each component is meticulously designed for its role in field control, stealth, and environmental adaptation. The result is a hull that is both robust and highly functional. The plasmonic metasurface skin is the outermost layer, responsible for broadband electromagnetic manipulation. Its golden ratio tiling supports non-reciprocal EM behavior, enabling radar invisibility and time reflection. The skin's impedance can be tuned in real time, making it a dynamic interface between the craft and its environment. The Dysprosium magnetic lattice is engineered for high-moment field shaping and inertial tensor control. Its rings and struts, spaced by Fibonacci radii, provide a stable framework for field manipulation and temporal cavity anchoring. This lattice is essential for both propulsion and stealth, enabling the craft to redistribute internal stresses and support non-reciprocal wave coupling. The acoustic metamaterial core is a Fibonacci-structured phononic lattice. It absorbs shocks, nullifies sonic booms, and enables underwater stealth. By converting mechanical energy into temporal cavity oscillations, this core supports standing wave formation and seamless environmental adaptation. The temporal modulation stack consists of rapidly switchable metamaterial layers. These layers create programmable time boundaries, enabling field inversion and stealth. The stack is integrated within the hull, working in concert with the other material systems to deliver unmatched control over wave interactions. The control stack manages variable frequency energy injection and Fibonacci-timed pulse trains. This system orchestrates the temporal boundary switching arrays, ensuring that the craft's stealth and propulsion systems operate in perfect harmony. The control stack is the brain of the craft, coordinating all subsystems for optimal performance. The temporal propulsion system leverages directional time boundary modulation and momentum gradient field shaping. By creating non-reciprocal coupling between electromagnetic and phononic modes, the craft achieves recoil-free thrust. This system is a radical departure from traditional propulsion, relying on field imbalances and temporal asymmetry for movement. The craft's environmental adaptation modes are tailored for land, sea, air, and space. Each mode leverages specific material and field configurations to optimize stealth, propulsion, and energy efficiency. The universal temporal envelope ensures that the craft can transition seamlessly between domains, maintaining operational superiority in any environment. Stealth and erasure are achieved through sensor scrambling, effluent nullification, observer erasure, and background temporal cloaking. The craft's metamaterial hull modulates time boundaries to return scrambled echoes, suppress ionized wakes, and blend into the ambient space-time background. These systems ensure that the craft remains undetectable and untraceable. The sensor scrambling mechanism uses time-reflected electromagnetic and acoustic waves to return echoes that defy object correlation. By modulating the hull's properties, the craft ensures that tracking algorithms receive inconsistent or impossible data, effectively masking its true position and trajectory. Effluent nullification is achieved by suppressing ionized wakes and thermal trails through acoustic and plasmonic inversion zones. This ensures that the craft leaves no coherent environmental residue, further enhancing its stealth capabilities. Observer erasure protocols ensure that external observers receive time-reversed interaction patterns. This makes post-event reconstruction of the craft's presence impossible, as the data appears as incoherent interference rather than a coherent object signature. Background temporal cloaking is achieved by modulating the craft's temporal boundary to match ambient field conditions. This allows the craft to blend into the background of space-time itself, making it virtually undetectable even to advanced sensors. The craft extracts energy from environmental electromagnetic fields, pressure waves, thermal gradients, ionized wakes, and even vacuum fluctuations in space. By harnessing these sources, the craft minimizes detectable emissions and supports closed-loop operation, making it both efficient and stealthy. Energy reuse is accomplished through temporal cavity compression, Fibonacci-timed pulse trains, non-reciprocal wave coupling, and time-reflected energy return. These strategies ensure that the craft operates efficiently, with minimal waste and maximum stealth. The ChronoLentis-Phi Framework integrates mathematics, physics, advanced materials, geometry, and temporal engineering. Each subsystem Dysprosium lattice, acoustic core, plasmonic skin, and temporal modulation reinforces the others, creating a coherent and original propulsion and stealth system. All described combinations of temporal metamaterials, Fibonacci structuring, Dysprosium lattices, and time reflection propulsion are original innovations by James Hartmann. This authorship and priority declaration ensures that the ChronoLentis-Phi Framework and the CL-Phi mirrored Seraphim craft are recognized as pioneering achievements in temporal aerospace engineering. The ChronoLentis-Phi dossier is designed for legacy and dissemination. Each schematic, equation, and subsystem is documented for future reference, ensuring that the innovations are preserved and recognized. The dossier includes cinematic posters, narration scripts, and time-stamped artifacts for public and scientific audiences. The Chapter 1 cinematic poster visually anchors the foundational architecture of the ChronoLentis-Phi framework. It features a realistic 4K lenticular craft cutaway, with all major components labeled temporal boundary modulation, Fibonacci shell geometry, material architecture, standing, wave cavity, and energy extraction systems. Authorship and date are explicitly credited to James Hartmann, January 2026. The Mathematical Foundations poster presents a blueprint blue background with glowing white field lines and equations. The transparent cutaway of the lenticular craft reveals internal standing wave cavities and the Dysprosium lattice with mathematical anchors orbiting the craft. This poster serves as the official mathematical schematic for the ChronoLentis-Phi dossier. The hull architecture cutaway poster showcases the internal structure of the ChronoLentis-Phi hull with realistic 3D depth and precision labeling. All major subsystems are visible, including the rapid time-modulated metamaterial shells, Dysprosium magnetic lattice, acoustic metamaterial core, and plasmonic metasurface skin. Authorship and date are embedded for legacy documentation. The Temporal Propulsion Field Map poster visualizes the propulsion physics of the ChronoLentis-Phi system. It highlights directional time boundary modulation, temporal asymmetry stress, differential wave pressure, and the momentum gradient vector. Non-reciprocal wave coupling and the time-inversion operator are also featured, illustrating the craft's unique approach to field propulsion. The Stealth and Erasure system poster captures the stealth physics and trace erasure mechanisms of the ChronoLentis-Phi system. It visualizes sensor scrambling, effluent nullification, observer erasure, and background temporal cloaking, providing a comprehensive overview of the craft's advanced stealth capabilities.